So I'm going to go ahead and start with our first question. It's been known for a long time that obesity is associated with certain types of cancer. For example, the seminal study by Cal et al. In the New England Journal of Medicine found that compared to normal weight individuals, obesity was associated with a higher mortality owing to malignancy in either sex. The most common were cancers of the esophagus, colorectum, liver, gallbladder, pancreas, kidney, even non-Hodgkin's lymphoma and multiple myeloma. However, almost 20 years later, the study by Cal, the cellular and molecular mechanisms underlying this association remain elusive, although hyperinsulinemia, hyperglycemia, sex hormones, adipokines, chronic inflammation, oxidative stress, and altered immune response are all believed to play a role. Further to these, are there any additional general pathomechanisms involved in the association of obesity and cancer that you would like to discuss?
Certainly. You can hear me okay, right?
Mm-hmm.
Wonderful. So yes, so my group has been studying this association between obesity and cancer for the past 10 or 15 years, and it's a fascinating field that's evolving dynamically. Speaking of the association between obesity and cancer, there are several fundamental distinctions that need to be emphasized. It's important to clarify what we're talking about. So when we talk about cancer, we can consider cancer risk and cancer progression, which are completely separate issues. So for certain cancers, obesity is more likely to predispose the patient to cancer, and that's cancer risk, the chance that the cancer will arise in an individual. And then you can consider the risk of cancer recurrence after the patient has been treated. There is a risk of cancer relapse, which obesity can also increase. And you can also consider various aspects of cancer progression to aggressive stages and the increase in cancer-associated mortality and morbidity and mortality that is associated with obesity. So depending on what we are talking about, the risk or the progression, the mechanisms may or may not be completely different, or in some cases they're similar. And also another important issue that needs to be emphasized is that for different types of cancer, the mechanisms underlying either risk or progression are also different. So it's really for each specific association of a particular cancer type with a particular stage of cancer, there is a completely different black box that we have to open and figure out the mechanisms for. So we are at early stages of figuring out how it all works. There are some fundamental mechanisms that underlie this fascinating biology and pathophysiology. And I can talk a little bit about all of those things, and I welcome you to interrupt me at any moment in case you have any questions as I talk, and I can clarify something on the spot before we proceed to the next question. So one type of cancer. So first of all, the cancers that are linked with obesity, by and large, are those that are surrounded by fat tissue, and there are exceptions, of course. Some leukemias and some blood cancers associated with obesity, and it's interesting to consider as to how this works. And but the progression of cancer, which is what my lab mainly studies, those are typically carcinomas that are surrounded by fat tissue and then are in direct contact with fat tissue. And fat tissue, or scientifically calling it adipose tissue, is what makes people obese, right? So it's the overgrowth of white fat tissue, which is made of adipocytes and other types of cells, such as stromal cells, vascular cells, and infiltrating immune cells. The overgrowth of adipose tissue is what obesity is. And just to define obesity more specifically, there are distinct types of obesity. There is healthy obesity and unhealthy obesity, generally speaking. So obesity predisposes to not only cancer, but also predisposes, of course, to cardiovascular disease and type 2 diabetes. And those are, heart disease is clearly the main killer before cancer. So some patients develop obesity without necessarily being predisposed to those diseases. And those are the minority. The majority of patients who become obese will be more likely to develop cardiovascular disease, type 2 diabetes, and certain types of cancer, and have those cancers more aggressive. And then there are two types of obesity in terms of where fat tissue overgrows. There is, you might have heard about apple-shaped obesity where belly overgrows, and then there is pear-shaped obesity where subcutaneous gluteal fat overgrows. And pear-shaped obesity in subcutaneous fat under the skin is typically more prevalent in women, and it's regulated by sex hormones, as you can imagine, and the apple-shaped obesity, which is overgrowth of abdominal fat, is more prominent in men, and this is the one that is typically linked with pathophysiology and predisposes to disease. And sometimes it develops in women as well, of course, and in certain and it has racial sort of specification. In some races, it's more prevalent than others. This apple-shaped obesity. So all of those nuances are important to consider. But coming back to cancer, we typically study the progression of cancer in carcinomas that are surrounded by fat tissue, and typically it's the proximity of fat tissue that stimulates the aggressiveness of cancers. And this is the case for prostate cancer. So prostate cancer in men, of course, is an interesting case of carcinoma for which there is no increased risk. Obese individuals are not more likely to develop prostate cancer, but they're more likely to have that cancer more aggressive and more lethal. Because of that, we've been studying the progression of prostate cancer and the mechanisms that are responsible for that. For other types of cancer, such as certain types of breast cancer, colorectal cancer, and endometrial cancer, it's the risk of cancer that is greatly induced, as well as the progression. So let's start talking about mechanism. So you've mentioned some of the mechanisms, high glucose, high lipids in circulation that could serve as nutrients for cancer cells. Cancer cells feed on those, so you would expect those to be important for tumor growth. Sex hormones, adipokines, which are cytokines and other growth factors that are secreted by cells of fat tissue. And the two most important ones that are key for cancer progression are leptin and adiponectin. Those are the two molecules that are specifically secreted by adipocytes and not other cells in our bodies. And it's really the ratio of leptin to adiponectin in our circulation which is predictive of cancer aggressiveness. So high leptin and lower adiponectin is what is typically seen in cases of aggressive cancer. Chronic inflammation is typically associated with cancer risk. Oxidative stress is typically associated with cancer risk. And that's not surprising because oxidative damage in cells is what is causing mutations and cell dysfunction, and that is what's mutagenic in the end. And altered immune response is what can make cancers more aggressive as well, because normally the immune system initially tries to suppress cancer development and progression, but fat tissue can blunt that response. And fat tissue is a very dynamic organ in terms of receiving certain types of immune cells. There are all kinds of immune cells are homing to fat tissue as it overgrows, and the pattern and the repertoire of immune cells in adipose tissue changes as obesity progresses. And this redistribution of immune cells and their repolarization of macrophages, repolarization of T cells, definitely modulates the activity of the immune system against the cancer. So it's not surprising that adipose tissue becomes immunosuppressive, so to speak, and enables cancer progression. So those are some of the mechanisms that you already mentioned. So I'm going to talk a little bit about other mechanisms that you have not mentioned that are at the forefront of the field, and this is what my group is studying, and other labs as well. So speaking of risk, what's really important to consider is the caloric overload that actually leads to obesity. So when you think about obesity, there is overgrowth of fat tissue, of course, but this overgrowth of fat tissue is typically driven by caloric surplus, caloric surplus, and insufficient physical activity. So when we eat more and move less, essentially, that's when we're predisposed to accumulating calories in our fat cells, and that's how obesity ensues. It's important to consider both the diet and the excess of adipose tissue in thinking about how this obesity condition promotes cancer risk or progression, because both are important. So as patients put on those extra pounds, they typically eat more, and they have more sugar, more glucose again circulating in their system. And in addition to feeding cancer cells when they arise, if you think about the risk of cancer before it arose, what happens is that all of our normal cells before any cancer, they have to burn and so extra calories. They have to deal with them, and they essentially are under pressure to the mitochondria that are dealing with all of those extra calories. They generate extra reactive oxygen species, because this is what mitochondria do when they're exposed to those calories, and that creates the foundation for extra genotoxic stress. So cells essentially get worn out, and as a result of that, there is DNA damage that's accumulating, and not only in DNA, but in other nucleic acids, lipids, lipid peroxidation. There are all kinds of changes that accumulate in the cell. In the end, there is, as a result of this chronic overeating over years, cells undergo senescence. Senescence is a state of cell cycle arrest when the cell can no longer divide because it's accumulated so much damage that it's dangerous for it to divide. It senses there are checkpoints in the cell that sense that there is so much DNA damage that if it tries to divide, it will the division will be incorrect, and that's when the cancer will actually arise. So the cell is trying to protect the body for a while, and it just sits there without dividing. But the problem with this is that the cell will not die. It doesn't undergo programmed cell death, and it starts secreting molecules that are inflammatory. There is cytokines such as tumor necrosis factor, interleukin-6, and other interleukins. And those cytokines, they start essentially poisoning the surrounding tissue. And this combination of inflammation as a result of the secretion of those factors and accumulation of mutations in the DNA, this is what in the end becomes mutagenic and carcinogenic. So this is how the cancer arises. So certain things that contribute to the development of senescence, as it turns out, is deregulation of circadian rhythms that are linked with obesity as well. So this is something that we've been studying in collaboration with another group led by Kristen Mehan in our center. So what's been found is that when patients or experimental animals overeat, circadian rhythms get disrupted, and obesity is linked with changes in circadian rhythms. So we lose this cyclic pattern partly of sleep, cyclic pattern of feeding, and we start, it becomes more fragmented, more sort of choppy. And as a result of that, progenitor cells that divide and become functional once a day or once a night normally in healthy individuals, they start firing up their divisions and activity more erratically. And as a result of that, cells of our body, again, wear out more quickly. You can imagine that cells wear out more quickly, partly as a result of telomere shortening. So this is something that my lab has been studying very actively. So telomeres are protective caps on the ends of our chromosomes. And every time an adult cell divides, telomeres shorten little by little. And if the cells have divided too many times, telomeres have become so short that the cell cannot divide anymore, because again, it will be mutagenic for the cell, and it undergoes replicative senescence as a result of that. So stem cells in our bodies, they express an enzyme called telomerase, and telomeres lengthen with every division. But at some point, adult stem cells, they lose telomerase, and they start, and eventually, after a certain number of divisions, they undergo replicative senescence. So you can imagine that in obesity, because you lose the circadian rhythms, and because cells start dividing more frequently, rather than once a day or once a night, they start dividing twice a day or twice a night, or all the time, you reach this state of replicative senescence sooner, and you accumulate senescent cells faster in your lifetime. And as a result of that, the tissues start deteriorating quicker, and this replicative senescence predisposes to cancer sooner. So all of those things, diet, obesity, they accumulate to push this forward. And currently we're trying to understand what types of diet promote this more rather than less. Definitely it matters what we eat, and it's been shown that certain types of diet definitely shorten the lifespan, partly through predisposing to cancer. And it's been shown that, for instance, branched-chain amino acids that are rich in red meat, those nutrients, they promote the expression of, they fire up the growth hormone, insulin growth factor 1 axis, and insulin growth factor 1, IGF-1, is one of the key growth factors that shortens our lifespan of all animals, not only us, starting with nematodes, to fruit flies, to mice, to people. Increased red meat consumption, increased circulation of branched-chain fatty acids, increased burnout of cells through upregulation of IGF-1. That really shortens our lifespan, partly through inducing cancer. And in obesity, IGF-1 clearly circulates at higher levels, and that's what very important. And finally, another thing that my lab doesn't study, but is very important to consider, is the changes on microbiome that are associated with obesity. So that's been a hot topic. Microbiota are essentially the bugs, the bacteria that live in our digestive system, and in fact, not only in digestive system, but even in tissues, in various tissues, they've been found to infiltrate tissues and modulate the activity of our adipose tissue, of other organs. So bacteria reach deep inside of our organs, and the repertoire of those bacteria, they clearly predispose people to obesity, and they also predispose people to certain types of cancer, and how the patient's response to treatment against certain types of cancer. So for instance, immune checkpoint blockade, which is the really hot new approach to cancer treatment, it really is more or less effective depending on what the profile of microbiome there is in a particular patient who is being treated. So all of those things are important to consider.
That is so interesting. And it's interesting how many levels of error are happening at the same time. Almost feels like you can't really escape the damage that's going to happen. So you've just like touched on this briefly, but I wanted to dive more into details about the specific types of cancers that your group has gained insight on, which are prostate, breast, and ovaries. Do you believe that these three different cancer types share any common pathomechanisms associated with visceral obesity?
Yeah, that's a great question. So visceral obesity is, of course, obesity due to overgrowth of fat around our, abdominal organs, right? So breast cancer that you mentioned among those three is not surrounded by visceral fat. It's so mammary fat is more like subcutaneous fat, right? So you really need we really need to consider breast cancer and ovarian and prostate cancers as separate types of cancer because they face different types of fat tissue. Yet all of those cases are the cases of direct proximity of fat tissue and the interaction with fat tissue. So as I mentioned previously, the prostate cancer is not the cancer that is induced by obesity, but it's more aggressive in obese individuals. So is breast cancer, so is ovarian cancer. So let's talk about progression of cancer for a little bit. So in these three types of cancer, obesity definitely induces cancer progression. And when we talk about progression of cancer, which means cancer aggressiveness, there are certain mechanisms that we need to consider. And again, there is not one mechanism which is responsible for aggressive cancer progression. There are several. And the first important mechanism is the factors that are released by fat tissue right where the tumor is. So fat tissue surrounds the cancerous cells, and then they become talking to one another, intermingling with one another. Those tissues become tightly connected at the border of the tumor, and that's where this crosstalk starts occurring. And fat tissue supplies nutrients directly to cancer cells that it faces. And the most important nutrient in this case is, of course, fatty acids. So the lipids that accumulate on adipocytes, triglycerides, are broken into fatty acids, and then those fatty acids are released from adipocytes, and they are consumed by cancer cells directly right there on the spot at the tumor margin. And instead of feeding on sugars, so there is this dogma that cancers consume sugars. So that changes in carcinoma. As cancers become aggressive, they actually start feeding more on fatty acids that they receive from adipocytes. And those fatty acids, they serve as a caloric supply for cancer cells. And they also serve as building blocks for membranes. As cells divide, of course, they need to build new cell membranes, organelles, and the plasmic reticulum, and other organelles. All of everything in the cell is built of membranes. So fatty acids are used for that as well. They're also used for cell signaling. So there are all kinds of utilizations for fatty acids that are recruited from adipocytes adjacent to cancer cells. So that's very important. And what's actually happening is that if you look at adipocytes that surround fat tissue, the tumor in the fat tissue, as the tumors grow, adipocytes become smaller and smaller, and lipid droplets become smaller and smaller. And there you see this dynamic sort of progression of tumors sucking out lipids of cancer out of fat cells. And in the end of this process, the adipocytes surrounding the tumor, they become completely delipidated. They go back to the state where they used to be stromal cells. So adipocytes differentiate from stromal cells. They're essentially fibroblasts that undergo adipogenesis, the process of differentiation into adipocytes. They start accumulating lipid droplets, and this is how fat tissue grows. So when carcinomas are progressing, this process is reversed, and the adipocytes go back from being adipocytes back to their progenitor status, where they're just fibroblasts. And you end up with a bunch of fibroblasts around tumors. And those fibroblasts, as we published recently, they start becoming recruited by cancer. So they start infiltrating the inside of the tumor. And we did it in collaboration with laboratory of Phil Sherry at UT Southwestern in Dallas. And also, in addition to those ex-adipocytes or previously, previous adipocytes, there are true progenitors, which are called adipose stromal cells, that serve as progenitors of adipocytes that are recruited from fat tissue into the tumors. And those adipose stromal cells also contribute to the population of cancer-associated fibroblasts. And this is what my lab discovered about 15 years ago. So several populations of cells from fat tissue are recruited by tumors, infiltrated inside the tumor, and they become perivascular stromal cells inside the tumor, and they do several important things. Initially, they promote tumor growth by supporting vascularization of the tumors. They secrete important growth factors such as vascular endothelial growth factor and other growth factors that endothelial vascular cells require for endothelial sprouting and vascularization. And tumors don't grow well without blood vessels. They need to be oxygenated. They need to receive nutrients through blood vessels. They need to dump waste through blood vessels. So without blood vessels, tumors don't grow well. And those cells from fat tissue, they contribute to vascularization, to stromal function. They help build an extracellular matrix, which serves as a scaffold for cancer cells. So they do a number of important things that support tumor growth initially. And later, what becomes important during cancer progression is that those stromal cells start doing more dangerous things because primary tumors, you can resect them or you can treat them with chemotherapy, and then you can temporarily stop cancer. The problem is cancer progression to metastatic stages. This is what really kills cancer patients. And the metastasis is the result of cancer cell invasion and dissemination. And this process is associated in carcinomas with the so-called epithelial to mesenchymal transition. So carcinoma cells are initially epithelial. They are secretory luminal, cuboidal organized cells. But then as the cancers become more progressive, they undergo the transition to fibroblastic state, and they become more invasive, and they whizzle out of their primary site, and they go traveling, and they create secondary sites of cancer, and this is what becomes incurable eventually. So the recruitment of adipose cells into the tumor promotes this process through important cytokines, and my lab discovered that CXCL12, also known as SDF1, stromal-derived factor 1, is one of the important cytokines, both in prostate cancer and in breast cancer and in ovarian cancer, has been shown by other groups. This cytokine promotes the epithelial to mesenchymal transition and promotes cancer metastasis. So, and there are probably other factors as well. There are probably other adipokines that are secreted by cells of fat tissue that promote those processes in those three types of cancer, and other carcinomas as well, not only those three. All cancers that are surrounded by fat, they can take advantage of those fat cells recruited by the tumor, infiltrating inside the tumor and promoting tumor growth first, and then cancer progression to metastasis later. And also it's paracrine signaling from adipose cells that on the spot promotes various carcinogenic and tumor progression processes. And also those factors go systemically as well. They adipokines, they're secreted into the circulation, leptin and adiponectin. Of course, you find them in circulation. So excess of fat tissue can also stimulate tumor growth distantly, of course. So it's not to say that it's always only locally. So that's why obesity is linked with a variety of cancers, because it can work through the distance.
Thank you for explaining that. So to move on, there was another seminal study in the Journal of Hepatology published in 2019. It was conducted on 4,722 adults with non-alcoholic fatty liver disease, compared to 14,441 age and sex-matched controls, and they were followed for a median of 8 years. So the study found that non-alcoholic fatty liver disease was associated with increased risk of cancers, most of which were affecting the GI tract. However, the association between obesity and cancer risk was small among those who did not have the disease, the non-alcoholic fatty liver, suggesting that it may mediate the association of obesity with cancer. What's the specific cellular and molecular underpinnings that could link this association of non-alcoholic fatty liver disease with cancer?
Yeah, so it's an interesting question. So yes, indeed, last year, in addition to the paper that you just called out, there was another study published that showed that bariatric surgery, which is essentially surgical manipulation of the digestive system that decreases food intake and reduces obesity dramatically, much more dramatically than other lifestyle interventions or diet or pharmacological treatment. So bariatric surgery significantly reduces the risk of any cancers, most cancers, and particularly obesity associated cancers in patients with NFLD and with severe obesity. So obese patients with this liver condition definitely benefit from reduced adiposity in terms of their cancer risk, and especially patients with cirrhosis. So cirrhosis is, precancerous fibrotic change in the liver, which predisposes to hepatocellular carcinoma. So those patients benefited the most. So the mechanisms are not really clear, and the disclaimer is that I'm not a specialist in liver or liver cancers, and I can only speculate on what could be happening. So liver is a cancer which is kind of different from the cancers that I had just talked about. Unlike prostate, breast, ovarian, and other reproductive cancers that directly intermingle with fat tissue, liver does not directly interact with fat tissue. It's kind of separated from it. So it sits there, but there are so many changes that liver undergoes in obesity that there are clear potential mechanisms that could be responsible for what could happen. So think about what liver does. Liver is a key organ that mediates glucose lipid balance and metabolism, and it produces all kinds of hormones and growth factors that mediate those pathways and insulin sensitivity or resistance in disease. So thinking about this, what happens in fatty liver disease is ectopic fat accumulation in liver cells and hepatocytes, right? And that happens for several reasons. There are certain, in certain cases, there are genetic factors that predispose to that, mutations or epigenetic changes in the expression of certain factors that regulate lipogenesis or lipolysis in liver cells directly. And that can result in ectopic lipid accumulation in liver cells and steatosis and fatty liver disease. But it also almost always seen in patients with obesity. So patients who overgrow fat tissue, what happens in them is that we get more fat cells as we put on extra pounds, but also our fat cells become larger, and especially when fat cells undergo replicative senescence, and when progenitor cells cannot divide anymore to make new adipocytes, fat tissue cannot sustain its size and grow in size anymore through division, through proliferation of progenitor cells and making new adipocytes. Instead, it starts growing or maintaining its size because there is cell renewal. So certain cells die and then the new ones will arise. So obesity is something that is very hard to treat because the body remembers how big it was once. And once you are 300 pounds, the body will try to keep you at 300 pounds. It's very hard to lose weight, as you know. And initially in kids, what you see is fat cell being small and our fat tissue built of many, many small adipocytes. If you look at older people, especially those with unhealthy obesity that predisposes to disease, instead you see large adipocytes. So there are fewer cells in fat tissue, but they're larger. And those large adipocytes, they become dysfunctional. They become hypoxic. They don't get enough nutrients. They don't get enough oxygen because of their size. The blood vessels that wrap around those fat cells are not sufficient to keep those cells alive. They also become brittle. They pop, and the lipid spillover that happens in fat tissue results in dissemination of those lipids systemically, and that's how we get steatosis in the liver, and also ectopic lipid accumulation in other organs, and in the pancreas, and the muscle. So that's in part, or mainly, how obesity really makes us sick is lipotoxicity that obesity induces as a result of this lipid containment dysfunction. So fat tissue is good. Its role in physiology is to contain lipids. It's a lipid rheostat. It's a reservoir of lipids that it keeps them in check. If you have a lipid overload, fat tissue takes them on, and it saves you from lipotoxicity. But when it becomes dysfunctional in obesity, then lipids spill over eventually, and that's when they will result in fatty liver disease, and the liver becomes dysfunctional because the cells don't work anymore when you have those fatty livers. Then gradually it leads to cirrhosis, which is accumulation of extracellular matrix in the liver, and cirrhosis, the fibrosis of the liver, and fibrosis of other organs as well is also carcinogenic, and inflammation. So all of those things in combination, they induce liver dysfunction, and as a result of liver dysfunction, everything changes. Metabolism changes. Probably expression of IGF-1 changes, and IGF-1, insulin factor 1, which is secreted by the liver, is a key carcinogen. Of course, microbiome changes, the immune system function changes, everything changes. So what's more or less important, we don't know yet, but probably all of those things synergize to predispose to certain types of cancers in fatty liver disease. So it's not surprising that if you prevent obesity and prevent fatty liver disease, then you'll prevent various types of cancers that are triggered by all of those mechanisms that I've discussed.
Okay, so you actually beat me to mentioning the study about bariatric surgery, but that's going to be my following question. So logically, if we admit that obesity predisposes to cancer, we're going to have to expect that targeting obesity would result in a reduction of cancer. So, and there was this study that was published in June of 2022, reporting that compared to no surgery, bariatric surgery was associated with a significantly lower incidence of obesity-associated cancer and cancer-related mortality compared to those with obesity. So would you like to discuss any non-surgical options that might potentially be conducive to the same beneficial outcomes as bariatric surgery?
Yeah, so this is really the future, thinking of how we can intervene and how we can break this link between obesity and cancer. So yes, there are some promising data on bariatric surgery, so it does decrease the risk of postmenopausal breast cancer. It's not as clear as to whether it's applicable to other types of cancer. Endometrial and prostate cancer data are kind of iffy. It's not very clear if it's the case. Women seem to benefit more from bariatric surgery than men for certain types of cancer. It's not clear why. Data on bariatric surgery and gastrointestinal cancers is kind of conflicting. So cancer recurrence and morbidity, in bariatric surgery is not clear. So maybe it works for certain types of cancer, but because bariatric surgery is only prescribed for really extreme obesity cases, we really need to think of other approaches. And other approaches to obesity are the natural approaches. It's the lifestyle intervention. It's weight loss through diet, through lifestyle changes, through exercise. And this is what we need to be thinking about, because all of those things reduce the risk of type 2 diabetes. And it's been shown that, so there was a paper recently studied that after 10 years, people who had reduced weight loss as a result of normal lifestyle interventions, they had a significantly lower risk for developing breast cancer compared to control group. So what types of, lifestyle changes are more beneficial than others? It's not very clear. Dietary changes are, there are many types that you can think about. There is caloric restriction that clearly induces a lifespan in various models and in people as well. If you eat less, you live longer, partly as a result of lower cancer risk. What's been talked about the most, calorie restriction is hard. What's easier to do and potentially as beneficial is intermittent fasting, when we stop eating for about 12 hours a day, and that may be very effective. So that's the best approach. For some people, it's hard. People are thinking about pharmacological approaches. There are no good data right now that anti-obesity drugs do anything as far as cancer is concerned. There are some, metformin is an anti-diabetic medicine which targets the MPK and mTOR pathway that has been shown in combination, not alone, but in combination, it seems to be suppressing breast cancer in certain clinical trials, but it's too early to say. Other anti-obesity drugs such as orlistat, which reduces lipid absorption in the gut and suppresses lipogenesis. There are no clinical data for whether it improves cancer outcome. And so we don't have good data on pharmacological approaches. Liposuction, which is basically sucking fat out from under the skin, is probably not a good idea. You can locally reduce the amount of fat, but the body will deposit it somewhere else, and it will trigger inflammatory responses that probably will backfire and not be beneficial in the long term. And finally, what needs to be thought about is also the late stages of cancer. So actually, cancer patients, they die of cachexia most of the time. Cachexia is body wasting as a result of not only, so initially a lot of patients are overweight or obese when they develop cancer, but as the cancer progresses, for many types of cancer, such as pancreatic cancer, which is also linked with obesity, patients become very thin, frail, and first fat tissue wastes, and then muscle tissue wastes, and overall there is this tissue wasting, the cachexia, which actually kills most of the patients. And it's important to consider the approaches that are used to break this link between obesity and cancer, to not take it too far and to prevent inducing body wasting. And one of the hot promising approaches to anti-obesity therapy is activation of thermogenic fat, brown fat or beige fat, which has been found in people. So fat adipocytes, they accumulate lipids, brown adipocytes, they burn lipids off, and this generates heat. So if you redirect adipocytes from white to brown, and there are approaches to do that now, then it's an approach to treat obesity and potentially an approach to prevent or suppress cancer. The problem is that it's been shown that activation of brown fat predisposes to cachexia development. So in some cases, this hypermetabolic response as a result of fat metabolism activation could be dangerous. So we need to be careful on how we deal with this.
Thank you so much. This was extremely insightful.